39th lecture, and our topic today is FIR, digital filter design by windowing. This is one of the most popular techniques for FIR filter design, and we shall discuss this in some details. In the last lecture, we had taken an example of a digital to digital transformation. We took a low pass filter and then transformed it to a high pass, a band pass and a band stop filter. And then we had started FIR design. We discussed the importance of FIR, why FIR, and also the disadvantages of FIR design as compared to IIR. And we said that there are only two analytical techniques which are available, and that too they are not completely analytical, they are semi-analytical. They only give you a rough idea of what it is going to be. You might have to undergo a number of iterations before you zero in on a particular design. One is windowing, the other is frequency sampling, and the third, of course, in common with IIR design, you have the computer aided design techniques which are very powerful. Nevertheless, they are not analytical, they are based on empirical procedures and algorithms. In FIR design, we had also said that the terminology used is slightly different. What we consider is that the pass band oscillates or varies between 1 plus delta 1 and 1 minus delta 1, and the stop band is at omega 2. Stop band transmission is delta 2. And we said that this can be easily transformed into our nomenclature delta P and delta S and vice versa, and the formulas are that you just normalize the highest response to 1. So, delta P becomes equal to 1 minus delta 1 divided by 1 plus delta 1, which by compendendo and dividendo you require delta 1 to be able to estimate the order required of the FIR design. So, given delta P, you convert to delta 1, which is 1 minus delta P divided by 1 plus delta P, and then delta 2, our delta S in our nomenclature shall be equal to delta 2 divided by 1 plus delta 1, which gives rise to delta 2 in terms of delta P and delta S. This is twice delta S divided by 1 plus delta P. And then the only formula available for estimating the order, unlike IIR design where NB and NC are given by analytical formulas, and you have to choose the integer higher than whatever value comes. Here only an estimate is available. There are complicated formulas. There is no point in using them, because after all you shall have to iterate a number of times. If the number that comes here does not suffice, then you have to increment it by 1. Then if that does not suffice, increment it by 1 more, and so on. And therefore, we shall use the simplest formula 10 log 10. This is also an approximation. The figures are 9.85 or something. 10 log 10 delta 1 delta 2, the product of the two, minus 15 divided by 14 multiplied by delta plus 1, where delta minus log 10. Is that right? That is correct. Minus log 10 delta 1 delta 2 minus 15, because this is going to be a small quantity, so log will be negative. Okay? And delta is, in our terminology, omega S minus omega P divided by twice pi. Obviously, for high pass filters, this is for low pass. For high pass, it is the same formula, except that delta will now be omega P minus omega S by 2 pi. What the formula transforms into in the case of band pass and band stop we shall discuss a little later. This I will have to dig into the literature. This is not available in either Mitra or Johnson. We will discuss this a little later. So, the philosophy of windowing is that given the required transfer function h d of e to the j omega, which if you have a low pass filter, if you want to design a low pass filter, then the desired frequency response, since you cannot design the filter analytically completely, therefore, there is no point in starting from what is given. You aim at the ideal. In other words, you assume that the magnitude of h d j omega follows the ideal filter, that is omega p and the finally pi. Okay? What is the reason? Because the design is not analytical, it is semi-analytical. In the case of IIR design, we could start from what is delta p, what is delta s, then estimate the order, then write the transfer function. Here we cannot do that. Therefore, we aim at this. We also aim, FIR design is most useful when you ask for linear phase, and therefore, what we assume is that h d e to the j omega is e to the power minus j omega tau. We want a linear phase, the magnitude should be 1, but the phase should be linear, omega tau, for magnitude omega less than omega p less than pi, and it is 0 otherwise. So, this is our ideal response. Okay? This is what we want. We did not bring in delta p, delta s or delta 1, delta 2 because it is not useful to do so. After all, when you get the design, we shall have to find the frequency response, check whether it satisfies or not, and then go back and so on and so forth. That is why the whole procedure is semi-analytical. So, what we do is we expand h d of e to the j omega in Fourier series. Okay? And in Fourier series, and in general the Fourier series is h d n e to the minus j n omega, n equal to minus infinity to plus infinity. In general, this is the story. Fourier series has infinite number of terms. Now, what you can, since infinite number of terms gives rise to an IIR filter, h d n becomes of infinite length, minus infinity to plus infinity. What we do is we arbitrarily truncate it at some point. Suppose we truncate it at n equal to minus m on the left side and n equal to plus m on the right hand side, then we get a filter of length twice m plus 1, and it shall be a 0 phase filter. Isn't that right? It will be a 0 phase filter because we have samples on the left and samples on the right. So, this would have been, instead of e to the minus j omega t, it would have been 1. But in any case, we cannot realize a 0 phase filter. Why? Because the filter is non-causal. H of n must be less than 0, must be equal to 0 for n less than 0, otherwise you cannot realize. Therefore, after we obtain this, we shall have to multiply the transfer function by z to the minus m anyway. So, why not start from n equal to 0 and go up to n equal to n minus 1, truncate it, alright, truncate it. Since we have assumed a linear phase, we started from the expansion of a linear phase transfer function, it is guaranteed that the impulse response h d n that we get shall be symmetric or antisymmetric depending on what you want. Okay? You might want j omega tau plus pi by 2, then it will be antisymmetric or with a negative sign. Okay? So, what we do is, there is no realizability problem if we start at n equal to 0, and therefore, this is what we use. Therefore, my h sub d of e to the j omega is approximated by h of e to the j omega, which is equal to summation n equal to 0 to capital N minus 1, the length is capital N, h d n e to the minus j n omega. It is as if the infinite length impulse response is allowed to pass through a window of rectangular shape. It is as if, well, you can write this as summation h d n times w n e to the minus j n omega, n equal to minus infinity to plus infinity, where w n is unity only between n equal to 0 and capital N minus 1. That is, w n is equal to 1, 0 less than equal to n less than equal to capital N minus 1, 0 otherwise. So, it looks like a window of length capital N through which the impulse response passes, and this window is rectangular in shape, right? Its amplitude is 1 for all values of n between 0 and capital N minus 1 and 0 otherwise. So, it looks like a window through which the total impulse response is passed. So, only the impulse response within this region n equal to 0 to n minus 1 that passes, all the rest are truncated, all the rest are made to vanish, all right. Now, there is no guarantee that you will get a good approximation, there is no guarantee, it is throwing a stone in the dark. Only thing you know an estimate of capital N. Therefore, this is a starting point, now you will have to iterate. So, this is why this design is called windowing technique. In other words, you expand in Fourier series and then truncate it at some point, starting from n equal to 0, truncate it at some point which looks like the total impulse response passing through a window. This window in this particular case is rectangular in shape. Now, rectangular windows have a number of disadvantages, and one of them is the so called Gibbs phenomenon. The name is Gibbs, it is not Gibb, it is not apostrophe s. The name is A. J. Gibbs phenomenon, and Gibbs phenomenon occurs whenever you want to approximate a discontinuity. You want to approximate a discontinuity like you have in a low pass filter or any ideal filter. If you want to approximate a discontinuity by a finite number of terms, Gibbs phenomenon occurs, and the phenomenon is the following: that there are oscillations around this region where the discontinuity occurs, and also around this region. In other words, the approximation is not smooth, is not monotonic. There are oscillations, and the last oscillation, last peak is important. The oscillations start building here and then go like this, then it comes down, then the first undershoot is the highest, then it goes like this. This is called Gibbs phenomenon, and it occurs even when the number of terms is infinity. It is a very peculiar phenomenon. Even when, in other words, the Fourier series is still not an exact representation of a periodic function. Okay? It is not an exact representation. If the function has discontinuities, for a smooth function like a sinusoid corrupted by third harmonic or fifth harmonic, yes, you will get a perfect approximation. But suppose the Fourier series is that of a function like let us say a rectangular wave like this, then even if you take infinite number of terms, it is still an approximation, because there are sharp discontinuities. And what you get in practice, if you take an infinite number of terms, is that you get a rod here. The rest of it is fine, but at this point of discontinuity you get a amplitude rise, and at the point of discontinuity here you get a fall. Okay. The amplitude of this rise or fall does not depend on the number of terms. Gibbs phenomenon has many peculiarities, and one of them is that the amplitude, that is, if you take 5 terms, 25 terms, 35 terms and 100 terms and 10,000 terms, the amplitude of the last oscillation before the discontinuity and the first oscillation after the discontinuity, they remain almost constant. For a sharp discontinuity like this, finite discontinuity, it is about 18%, that is 1.178. that would be the value here. If this value is 1, then that value would be 1.17, 17.85%. Approximately we take it as 18%. And this is the reason why we do not use rectangular window unless we are forced to, unless the specifications are relaxed, that 18% tolerance can be tolerated. To show the Gibbs phenomenon, I shall project a diagram here which shows the Gibbs phenomenon in effect. This is an approximation of a low pass filter, that is, we take e to the minus j omega tau, and then this is the picture for capital N equal to 25. We have plotted the magnitude, so we do not show undershoots. Okay? No undershoots, these are overshoots. Or magnitude negative becomes positive. Okay? Now you notice that the value above unity, the last peak here and the first peak here, they are almost of the same amplitude from the steady value, and this is what 1.178. Then this is capital N, the length is 25, the length here is 51. You notice that what has happened is there are more oscillations here, because we are using higher harmonics. Okay? But this amplitude and this amplitude almost remains constant, not exactly, it almost remains constant. Similarly, then this is increased to 101. You see there are more oscillations here, but this amplitude and this amplitude remains the same, and this is 151. When you go to infinite number of terms, it will come straight, oscillations will hardly be detectable, but there would be a rod here and a rod here. Okay? So this is what Gibbs oscillation is, and therefore we require to do something about the window. Instead of the rectangular window, one of the reasons why this occurs is that the window itself is sharp window, suddenly rises. N equal to -1 it is 0, n equal to 0 it rises to 1, okay, and then suddenly falls. So people are good at the initial stages that if the rise and fall of the window is smooth, it is not that abrupt, perhaps we shall get better results, perhaps we shall be able to avoid Gibbs phenomenon to a large extent. In other words, the window requires to be tapered towards n equal to 0 and towards n equal to capital N minus 1. But before we look at specific windows, let us find out what should be the ideal window or what should be the optimum window. Okay? You see, we have we have capital H of e to the j omega, that is the approximation of h d of e to the j omega, that is, we have already taken n equal to 0 to capital N minus 1 h d n w n e to the minus j n omega. Let us not specialize w n to rectangular. We want to find out what kind of window shall be the optimum. What are the characteristics of the window function? Okay. Yes, we have to have a finite impulse response, that is h of n, which is h d of n multiplied by w n. H d n is of infinite length, but w n must be finite. Okay. W n okay. I can write this as summation h d n w n e to the minus j n omega, if that is your objection. I take from n equal to minus infinity to infinity, but I choose my w n such that I get an FIR. That is, I must choose w n equal to 0 for n less than 0 and n greater than n minus 1. That is why these two are identical. But the second formulation now will help me in finding out what should be the optimum w of n. Let us look at that. I can write this as summation n equal to minus infinity to infinity. I replace h d n by the inverse Fourier transform relationship, which is 1 over 2 pi minus pi to pi h d of e to the j omega. Then let us make it, let us change the variable, because I have another e to the minus j n omega. So let us change the variable to theta. It does not matter, because we are going to integrate with respect to theta. So this is h d n multiplied by w of n, then e to the minus j n omega. Please distinguish between w and omega. W I write with a string here. So now we apply our usual trick. The summation is over n and the integration is over theta. Integration is a continuous variable, summation is over a discrete variable, they are not related to each other. So interchange the summation and integration. In other words, we write h of e to the j omega as equal to 1 over 2 pi integral minus pi to pi h d of e to the j theta. Then I bring this summation w of n e to the minus j n omega minus theta. Is that okay? N goes from minus infinity to plus infinity. Then we must have d theta. Agreed? Now what is this? If there was only e to the minus j n omega, it would have been capital W of e to the power j omega. Now since it is omega minus theta, therefore we shall have capital W of e to the j omega minus theta. Okay. So h d e to the j theta d theta minus pi to pi 1 over 2 pi, that is what it is equal to. And if you look at this integration, isn't this complex convolution? Right? It is. Therefore, the realized frequency response is the complex convolution of the desired frequency response and the windowed frequency response. Okay. I can also write this as 1 over 2 pi. Because it is a convolution, I can write this as W of e to the j theta okay, hd of e to the power j omega minus theta, because convolution operation is commutative. It does not matter what we convolve with whom. Okay. Now this gives us a clue as to what the window function should be. You what you want is that h of j omega, h of e to the j omega should be equal to hd of e to the j omega. Isn't that right? That's what we want. Now that is obtained obviously when w of e to the power j omega is equal to delta omega, 2 pi times delta omega. 2 pi we bring because there is 1 by 2 pi. Suppose w of e to the j omega, that is the spectrum of the window function, suppose it is 2 pi delta omega, in other words it exists only at omega equal to 0, then what does this integral become? It becomes simply hd of e to the j omega, right? Therefore, what we should aim for is a window whose spectrum is a delta function. Now that is not surprising, because if w of e to the j omega is equal to twice pi delta omega, then what is w of n? It is 1 for all n, isn't that right? In other words, there is no truncation. W of n equal to 1 for all n, therefore it becomes again an FIIR filter. This is therefore this result is to be expected, but this way of deriving the result points out that what we want for the window function is that it should be an approximation to the unit, an impulse of strength twice pi. It should be an approximation. In other words, we should have something like this. It should be an approximation to an impulse function, okay, and then all such approximations shall have side lobes, and therefore we shall have something like this. If we can get a window whose spectrum is like this, in fact rectangular window has a spectrum like this, right? Except that we don't want it because there is a lot of Gibbs phenomena. We want to smooth it out. So what is an optimum window function? There is no optimum. There is no optimum. We have to have a window function which approximates an impulse, okay, in the frequency domain. This is our aim. With that end in view, various windows have been tried, and we shall go through this list and their performance one by one. The rectangular window first. Rectangular window, that is w of n is equal to 1 for 0 less than equal to n less than equal to n minus 1 and 0 otherwise. The spectrum is capital W of e to the j omega. You can sum it up and show, we have done this earlier, that it is minus j omega n minus 1 by 2, then sine divided by sine. So sine of omega n by 2 divided by sine of omega by 2, and the spectrum is something like this. You get this is the magnitude and this is versus omega. The first 0 shall occur at not at omega equal to 0. At omega equal to 0 the value is capital N. At omega equal to 2 pi by n. The next 0 shall occur at 4 pi by n, and so on. So what we want is, in terms of this spectrum, what we want is that the main lobe width MLW What is it here? 4 pi by n. Okay. Main lobe width should be as small as possible. We want an impulse function. And this height, side lobe height SLH, should be as small as possible. Okay. This should be as small as possible. These two requirements unfortunately are contradictory. That is, if we want to increase the main lobe width, if we want to decrease the main lobe width, then capital N should increase. As capital N increases, it shrinks, but at the same time the side lobe height increases. In fact, the ratio of the main lobe height, which is capital N, divided by, you see, if capital N increases, this also increases. That's good. It will resemble more like a it will resemble an impulse function, but the side lobe height also increases. The ratio is approximately a constant. So this is the problem in FIR filter design. Whatever window you choose, it will be a compromise between main lobe width and the side lobe height, and there is hardly much of a choice except two windows which we shall not discuss in details in the class. One is the Kaiser window and the other is the Dolph-Chebyshev window, the idea of which is taken from antenna array design. In antenna array there are Dolph-Chebyshev arrays. The idea of in FIR filter design, this concept has been transferred. Now Kaiser window involves Bessel functions of order 0, and normally if it is to be an industrial design, a sophisticated design and so on, we shall use Kaiser window, but normally for ordinary applications other simpler windows which are easy to calculate and incorporate in design are used. Okay. Let us look at some of these simpler windows. One of them is the modified rectangular window, which says that instead of starting from 1, why don't we start from half? You know, it's an attempt to taper the window. We start from half, then all other things are 1 and so on. The last one, this is 0 and this is n minus 1. The last one is also half and the others are all 1. This is a modified rectangular window, as taper has been introduced, half here and half here. This, as expected, reduces the side lobe but increases the main lobe width. Okay. The next window that we talk about is the Hann window, Hann, H-A-N-N. Hann window is a smooth window, no abrupt discontinuities. It is half 1 minus cosine of 2 pi n divided by capital N minus 1 for 0 less than equal to n less than equal to n minus 1 and 0 otherwise. If we plot it, the plot looks like a cosine wave. Okay. It is half minus this, it goes like this and falls like this. And you notice that for small n equal to 0, the value is 0, and for small n equal to n minus 1, again the value is 0. Therefore, the end points are 0. The maximum occurs when this quantity is equal to pi. Cosine pi, 1 minus cosine pi will be 1 minus minus 1. So 2 by 2 is 1. So maximum value is 1, and it occurs at small n equal to n minus 1 by 2. Obviously, capital N is to be preferred odd value. There is another reason why capital N odd should be preferred, because the delay is then an integer. Half delay is very easy to accommodate in a DSP. So capital N is required to be odd. Now what happens if we apply such a window, that is the desired HDN is multiplied by WN like this? The result is something like this. You see the main lobe width, this is for capital N equal to 7, length equal to 7, and this is for length equal to 25. When you increase the length, the main lobe width shrinks, but the side lobe height increases. Here the scale is 0, 2, and the scale here is 0.5. Okay. Not only that, compared to the rectangular window, for the rectangular window the main lobe width is 4 pi by n. 4 pi by, if capital N is 7, then 4 pi by 7 is how much? 4 into 22 divided by 49, right? 88 by 49. How much is this? 1 point something, okay? Approximately 1.8. All right. Now what is this? What is the main lobe width here? About 4 radians. You see how much it has increased? Okay. It can be decreased by this. This is 1 radian below that of the rectangular, but the side lobe height increases as compared to capital N equal to 7. It is still smaller than the rectangular window, and that is where it counts. Rectangular window is hardly ever used. So window design, the other point to notice about hand window is that effectively the length is capital N minus 2, isn't that right? Because 2 of the samples are 0, 2 of the impulse response samples would be 0. The length was capital N, 2 gone, so it becomes N minus 2. You are not being able to utilize the efforts that you have put in aiming for a length capital N. The effective length becomes N minus 2. The next window that we consider is the so called Hamming window. Hamming window. You notice that hand window is half minus half cosine of 2 pi n divided by n minus 1. Okay. What Hamming did was, instead of 0.5, this is hand, both are 0.5. So Hamming used, instead of half, he used 0.54 for the first term. Naturally for the second term you have to use, because the maximum is 1, 0.46 cosine of 2 pi n divided by n. The advantage of this is that you are utilizing the full length window. The length, you see, at small n equal to 0, W of 0 is 0.08, and this is also the same as W of n minus 1. So instead of rising from the base of 0, it is a cosine shaped waveform. It is as if it has been raised, okay, by the amount 0.08. So Hamming window is also called raised cosine window. Raised cosine window. And the effect of increasing the length of the window is very similar to hand window, except that Hamming allows for a little more reduction in side lobe height. This is for n equal to 7, and you notice that the main lobe width has increased beyond 4 radians. Isn't that right? Minus 2 is here, 2 is here. It is increased beyond 4. It can be decreased to approximately 1 if you raise the length to 25, but then the side lobe height also increases. So it's always a compromise. It's always a compromise between main lobe width and side lobe height. Whatever is acceptable to you, you try the windows, and whatever is acceptable, you use that. These windows are simple because they are very easy to calculate. On the other hand, for Kaiser and Dolch-Chebyshev uses Chebyshev functions. So you require a table, or you have to calculate every time. Similarly, the Bessel functions also need to be calculated. They are tabulated, but not for all values. Obviously, they cannot be tabulated for a continuum of values. But these values, cosine function is very easy to calculate. Okay, the next window that we consider is the so-called generalized Hamming. There are very smart people, particularly PhD students. They said, why 0.54? What is so sacred? Use alpha. So he said, generalize the Hamming window as alpha minus, the next one must be 1 minus alpha. Okay, 1 minus alpha cosine of 2 pi n divided by n minus 1. Generalized Hamming window, where alpha you now vary to suit your requirements. And the what happens is, if we vary alpha, the window changes shape like this. I have shown here for alpha, all three that I will show have a length of 7. This is alpha equal to 0.3. You see the shape of the window, shape of the spectrum. It's not an approximation to an impulse. Our main aim, we should not forget, it should be an approximation to an impulse. There is a dip here. The dip starts disappearing when alpha is increased. As you know, alpha equal to 0.5, there is no dip, it is a cosine wave. So alpha equal to 0.4, there is still a dip, but a smaller amplitude, and when alpha increases beyond 0.5 and higher, there is no dip, there is only one main lobe, and this is the story for alpha equal to 0.9, considerably higher than the value used by Hamming. And once again the same phenomenon, the main lobe width decreases, but the side lobe height increases. Next, a gentleman by the name Bartlett, he said, if that is the story, why don't you use a simple window? Why cosine and raised cosine and so on? Why don't you use a triangular window? So he suggested that we use Wn as equal to I'll write the Wn equal to twice n divided by n minus 1, 0 less than equal to n less than equal to n minus 1 by 2, and 2 minus 2n divided by n minus 1 for n minus 1 by 2 less than equal to n less than equal to n minus 1. You see the point? It rises in along a straight line, then it falls along a straight line. No calculation, calculation is very simple. Why don't you use that? Okay. But in common with the hand window, it has the disadvantage that the end things are 0. Okay. And the maximum amplitude is of course 1. And this occurs at n minus 1 by 2 and so on. It is called a linear window or a triangular window or a Bartlett window. Bartlett is the proposer of this. And the there is one, it is not an advantage, a distinctive feature of the Bartlett window is that being triangular, because of the shape, it is very simple to calculate. Number 2, the spectrum is always positive, that is the pseudo magnitude is positive, it does not undershoot. I think I have made a mistake in these figures. I have shown these as magnitudes. This should actually be pseudo magnitudes. Okay. In the figures that I have projected so far, it should be pseudo magnitude. I have shown this as magnitude. This is mistake. Here also I should have deleted this magnitude signs. They are pseudo magnitude, but the pseudo magnitude here is positive, and therefore it is as good as magnitude. Similarly, when capital N is increased from 7 to 21, once again the same phenomenon, the side lobe height increases, but the main lobe width decreases. So there is nothing much to choose between Hahn and Bartlett. Okay. Hamming, there is something to choose because you are utilizing the full length. The other windows, many other windows have been proposed and they are still being proposed. One is the Blackman window. Blackman suggested that why do you use only one cosine? Why don't you use its second harmonic also? That is, Blackman suggested using 0.42 in some mixture minus 0.5 cosine 2 pi n divided by n minus 1. Then you use a 0.08 cosine of 4 pi n divided by n minus 1. So that the maximum still remains 1. Okay. When small n equal to n minus 1 by 2, this becomes plus 0.5, this becomes plus 0.08. So maximum is still 1. Well, there is no reason why you cannot extend further and complicate your life. But then this is not, it is not worth doing, because there is a kind of an uncertainty relationship between the main lobe width and the side lobe height. Okay. If one improves, the other deteriorates, and this is a reflection of the famous Heisenberg's uncertainty principle. It shows its teeth in many situations in in electrical engineering. For example, time bound and band limited functions. If a function is time bound, time limited, it cannot be band limited. Okay. The more it is time limited, the more is the spread in the frequency domain. It shows its teeth here. It shows its teeth in amplifier, rise time and bandwidth. The smaller the rise time, the larger is the bandwidth that you require. Okay. And bandwidth is a very costly phenomenon. So this is also an uncertainty relationship. Then the Dolph-Chebyshev window requires Chebyshev functions. The Kaiser window uses the Bessel function, and the relationship is I0, the argument is beta square root of 1 minus twice n by n minus 1 whole squared. You see how complicated it is. It is simply in computation. Once these are tabulated, then you see the Bessel function can be calculated in terms of an infinite series, and you see the complication of the computation. Usually in the infinite series can be truncated by 20 or so terms. The error is negligible, but even calculating 20 terms is a problem. So this has to be, you have to write a separate program for this, for the particular situation, and do it. So we will not go into this, but you notice that in all these windows there is something that we took care, that is Wn, it's a symmetrical window. Wn we had taken as equal to W of n minus 1 minus n. Why?
Linear.
Because of linear phase constraints. Okay. Hdn, if you want linear phase, Hdn is symmetrical. Therefore, whatever function you multiply Hdn by must also be symmetrical, otherwise linear phase shall not be maintained. Now we take a specific case, let us say a low pass design. FIR low pass design. So what we want is Hd of e to the j omega is equal to e to the minus j omega tau for omega less than omega p, which is less than pi, and 0 otherwise. This is the ideal low pass filter. Okay, we aim at this. When we want tau, obviously we have fixed our capital N. Isn't that right? What should be tau? Tau is capital N minus 1 by 2. Once tau is given, you have no choice. Only thing you can play with are the window functions. Isn't that right? Okay. So let us see what this gives. If you find Hdn corresponding to this, you have to use the inverse Fourier formula, that is 1 over 2 pi integral minus pi to pi Hd of e to the j omega e to the j n omega d omega. And if you substitute this, and the lower limit shall be substituted by minus omega p, upper limit would be plus omega p, Hd e to the j omega by e to the minus j omega tau, and therefore it is a very simple integration, exponential. And I would omit the intermediate steps. Hdn becomes equal to sine of omega p n minus tau divided by pi n minus tau, provided n is not equal to tau. Agreed? If n is equal to tau, then obviously this will be omega p not 1, omega p by pi for n equal to tau. When is this possible? Small n, this is possible only when tau is an integer, right? Tau is an integer, and therefore capital N odd. For capital N odd, n equal to tau or n minus 1 by 2, the value should be omega p by pi, otherwise it is sine of this. Now if I want Hdn to be, well, we started with linear phase, isn't it? We started with linear phase and said tau must be equal to n minus 1 by 2. You can prove it that if we start with e to the minus j omega tau, you can prove that tau must be equal to n minus 1 by 2. It is very simple. What you want is that Hdn should be equal to Hd n minus 1 minus n. Agreed? This is our requirement. Therefore, sine of omega p n minus tau divided by pi n minus tau should be equal to sine of omega p n minus 1 minus n minus tau divided by pi n minus 1 minus n minus tau. And this is possible only when this quantity is the negative of this quantity. right? They could be equal, but if they are equal, then you see they are equal only for a particular value of n, right, which is not what we want. They should be equal independent of the value of n. H d n should be equal to h d of n minus 1 minus n. Obviously, they are equal if small n equal to n minus 1 by 2. Isn't that right? That is for one specific value of n. We want this relationship to be valid independent of n. Therefore, the relationship is n minus 1 minus n minus tau should be equal to n minus tau, and this gives rise to tau equal to n minus 1 by 2. I beg your pardon, I did not use a minus sign, yes, minus of this. So, it is a proof of, it is a corroboration of what we have been talking about, that for linear phase tau should be equal to n minus 1 by 2. Now, therefore, if we use a rectangular window, then h d of n, rectangular window of length, let us say 7, which means tau equal to 3, and h d of n should be equal to sine of, let us say, omega p equal to 1 radian, not 1 radian per second, 1 radian. We are working out an example now. We shall work out this example with various windows and see what the effect is. Suppose omega p is 1 radian, then sine of n minus 3 divided by pi n minus 3, n not equal to 3, which gives rise to, with rectangular window, h d n is the same as h of n. Okay. So, h d of 0 shall be the same as h d of what? It has to be symmetrical. So, 6, 7 minus 1 is 6, that should be equal to sine of 3 divided by 3 pi. This 3 is in radians, and this comes out as 0.01497. h d of 1, which is the same as h d of 5, should be equal to sine of 2 divided by 2 pi, and that comes out as 0.014472, and h d of 2 equal to h d of 4 sine of 1 divided by pi. Do you understand why the negative signs do not appear? Because both are negative, numerator and denominator, and this comes as 0.26785. And finally, h d of 3 is 1 over pi. If n equal to 3, it is simply 1 over pi, and that is 0.31831. We will show next time how the frequency response looks like with this kind of a window.